Hi, I'm Jongseok at Sungkyunkwan University. It's a great honor for me to present our research on per-core scalable journal design today. This was achieved through close collaboration of researchers at Sungkyunkwan University and Samsung Electronics. JVD2 is a generic journal layer, which was designed to be used with any conventional file systems. Currently, the ext4 is using the JVD2 as its journal layer. As you can see in this figure, the JVD2 has a centralized design. That means no matter how large a system is, it has only one single journal structure in use. In JVD2, there is a single learning transaction in memory. A buffer represents an in-memory copy of a file system block. When a buffer is modified, the modified buffer is recorded in the running transaction first. When a transaction is closed by a fsync operation or timeout, it's changed to a committing transaction. Then, JVD2 begins committing the committing transaction. Naturally, this centralized journal design can be a significant scalability bottleneck. First, buffer modifications done by all cores in the system must be serialized at the journal layer, especially when a core tries to insert its modified buffer in the learning transaction. The core must acquire the lock to the learning transaction in advance. Second, because every write to the underlying storage device is serialized at the committing transaction, the JVD2 cannot fully utilize the internal parallelism of modern SSDs. We are not the first one to tackle journal's scalability issue. Some researchers proposed approaches that can parallelize the accesses to the in-memory journal structures or parallelize committing operations. However, because these approaches partially parallelize the current journal design, scalability bottlenecks remained here and there in the journal layer. For obtaining good scalability, two novel file system designs have been proposed. Their journal layers, of course, are scalable. However, the journal layers of these file systems are tightly coupled with the file systems, which are radically different from the current file system design. Many people want to continue to use the matured and verified file systems, because reliability is more important criterion than performance when choosing a file system. Therefore, we need a way to fully parallelize the current generic journaling layer. The most intuitive way to realize the fully parallel journal is making every core have its own independent journal. However, this induces a complicated consistency issue. Suppose that core 0 modifies file A and core 1 modifies file B. Buffer 1 is for the metadata block that have both metadata of file A and B. Again, let's assume that core 0 finishes its modification earlier than core 1. Buffer 1 in the core 1's journal will have both modifications from core 0 and core 1. For some reason, journal 1 can be committed earlier than journal 0. This can happen because they work independently to each other, right? After journal 1 finishes commit and while journal 0 is committing, a crash may occur. In such case, the committed buffer 1 holds the modification both from core 0 and core 1. Core 1's modification may persist. However, core 0's modification has never been committed. It's incorrect that buffer 1 has core 0's modification at its final state. In order to fully parallelize the journal layer, we need a journal coherence protocol for these parallelized journals. Our approach, Z-journal, provides fully parallel per-core journaling with the journal coherence protocol. I'm gonna briefly introduce the journal coherence protocol here. If you are interested in the rest of the performance optimizations as well, including proactive frozen copy and core-aware block group allocations, please refer to our paper. Order-preserving transaction chaining lies in the core of our journal coherence protocol. Please remember this. The final state of a file system block is formed by checkpoint, not commit. However, a block modification becomes persistent after it's committed. The ground rule is simple. We can checkpoint a modification of a buffer only after all of its preceding modifications become persistent. If this rule is well kept, no aforementioned consistency problem will occur. In order to do so, we need to record the write order to the buffer in the journal as well. For this, Z-journal maintains a transaction chain graph for the committed transactions. This transaction chain graph shows the precedence relationship between transactions. The graph is formed during the commit process. When performing checkpoint, Z-journal refers to this graph to check whether a committed transaction can be checkpointed safely. These transaction chain graphs are constructed based on chained transaction lists and marks. A transaction ID is unique within a core. Therefore, a pair of transaction ID and the core number can be used as a unique identifier of a transaction system-wide. A chained transaction mark is a pair of core number and transaction ID. The meaning of a transaction mark is the transaction ID of core number must precede the transaction that has the mark. For example, in this figure, transaction 4 of core 0 has 1,7 in its chained transaction list. This means transaction 4 of core 0 cannot be checkpointed before transaction 7 or of core 1 is committed. In this case, the chain is bidirectional. This means transaction 7 of core 1 also has 0,4 in its chained transaction list. This bidirectional relationship means both transactions must be considered as a single per transaction during the checkpoint stage. Unlike this relationship is unidirectional. That means transaction 2 of core 2 can be checkpointed regardless of transaction 7 of core 1's status, because this precedes this. The order in which this graph represents does not need to be followed at the commit process. So, each core can independently commit its committing transaction regardless of other core's activities. In addition, a chained transaction list uses a lock-free data structure so that a core can leave its transaction mark in the list of other cores' journals without acquiring a lock. Before explaining journal coherence checkpoint, I will explain the checkpoint method of conventional journaling scheme. When the commit is completed, the transaction changes to the checkpoint state and is inserted into the list where the checkpoint transaction is gathered. At this point, all buffers in this transaction are marked as dirty flag. The kernel thread that performs write back periodically moves these dirty buffers into the file system area and changes them to a clean state when they are completed. There is always only one original buffer with up-to-date status in the checkpoint transaction, so the order in which it is written is irrelevant. Z-journal's journal coherence checkpoint also marks buffers as dirty to be checkpointed, and it's the same as before that the write back thread works on. However, unlike before, buffers of committed transaction are not immediately marked as dirty. In other words, as I said before, not all committed transactions are objects of checkpointing. Instead, we add a valid state to the transaction in Z-journal. A transaction is valid when a transaction without a preceding transaction is valid, and all of its preceding transactions are valid. Z-journal marks the buffer included in the transaction in the valid state as dirty, and only checkpoints the valid transactions. Traversing the transaction chain graph is necessary to check that the transaction is in a valid state. I want to show this process through this figure. First, let's check if transaction 2 is valid in this figure. Because transaction 2 has no dependence, it's valid if it's committed. For transaction 3, it has a unidirectional chain relationship with transaction 2. At this point, transaction 3 itself is committed, and transaction 2 is valid, so transaction 3 is valid. Lastly, let's check the transaction 4. First, check if transaction 4 is a commit, and check whether transaction 3, which is a unidirectional relationship, is valid. Next, we need to check whether transaction 5, a bidirectional relationship, is valid. For this, we check the commit status of transaction 5 and check whether transaction 6 is valid. Then, both transaction 4 and transaction 5, which are bidirectional relationships, have both commits confirmed. and all other transactions except for these two are validated. So both transactions are valid. A committed transaction stored in a journal area has three kinds of blocks the same as JVD2: transaction descriptor blocks, data blocks, and a commit block. In Z-journal, the commit block also stores the chained transaction list of the transaction. In addition, the commit block also has the timestamp of the commit start time for the global ordering of transaction commits across multiple journals. The recovery process first searches for the transaction with the commit block from all journals to find the valid transactions. After this, it creates the transaction order graphs based on their chained transaction lists. Similarly to the checkpoint procedure, the recovery process traverses the graph to find valid transactions. Finally, the recovery process compares the timestamp of both transactions to determine the latest buffer images to restore. This table shows the system configurations used for the evaluation. We presented the results collected in the journaling data mode because they showed the performance benefit more vividly. We implemented Z-journal in the Linux kernel and modified the ext4 file system to recognize per-core journals and to use Z-journal instead of JVD2. We measured the performance and scalability of the Z-journal and ext4 combination while executing FxMark, Filebench, and SysBench. I'm gonna briefly show results of FxMark and Filebench. The write workloads of FxMark consist of the low and medium sharing level. In the low sharing condition, each core performs the target file operation for private files in its dedicated directory. In the medium sharing level, the override workload lets all cores access the same file, and the other workloads perform the given operation in the same directory. We experimented with no journal, JVD2, and Z-journal respectively on override workload. This graph was a result of low sharing override. It was the most favorable workload in FxMark, because this workload is where the file system scalably performs, but the resulting performance is poor for the serialization at the journal layer. This graph was the result of medium sharing override. The file system scalability was poor due to sharing, and the performance of the journal layer was also poor for the same reason. Even in this case, Z-journal gained 30% of performance improvement at 80 cores compared to JVD2 through its parallel journaling mechanism. To access the performance impact of Z-journal in the environment, which has a mixture of reads, writes, and metadata operations, we used the file server and barmail workload of Filebench. Since a large number of cores repeatedly created and updated files in a small number of directories, the throughput of JVD2 peaked at 10 cores and decreased as the number of cores increased. Z-journal showed significantly better performance than JVD2. Especially, Z-journal achieved 315% performance improvement at 20 cores. Barmail also showed a similar throughput change pattern with file server, and Z-journal improved performance by 58% at 80 cores. However, unlike file server, Barmail frequently called fsync, and the performance improvement for fsync by Z-journal is smaller than that for other file operations. Therefore, the performance gap between JVD2 and Z-journal was smaller than that in file server. In both experiments, Z-journal performed best at 20 cores, and performance gently declined beyond that point due to the NOMA effect resulting from the rapid increase in remote memory access across domains. This is conclusion. Z-journal increased scalability by placing journals by core, allowing each core to perform journaling independently. Z-journal includes a journal coherence mechanism, which provides complete parallelism for unshared buffer modification, and guarantees cache consistency by order preserving transaction chaining for shared buffer modification. Our evaluation showed that through its per-core journaling design, Z-journal is faster and more scalable than the current JVD2. Thank you for listening to the presentation.